Chapter number 3, Kinetic Theory of Gases and Radiation. Today we define or give the root, mean square, that is RMS speed or velocity. Discuss about the root mean square, RMS speed or velocity of the gas molecule or particles. In previous lecture, we derived the relation of pressure, equation of pressure of ideal gas is P is equal to 1/3 Nm upon V into V bar square. Therefore, V bar square, or this can be written as 3PV is equal to Nm into V bar square. Therefore, V bar square is equal to 3PV upon N into M, where this V bar square is the mean square velocity, P means pressure, P means volume, N means number of gas molecules, and M means the mass, total mass of the gas molecules. Now put N T is equal to 1/3 Nm, or we get the V bar square is equal to 3PV upon Nm. Now we use the ideal gas equation, that is PV is equal to nRT. Therefore, instead of PV we can put nRT. Therefore, P bar square is equal to 3 into nRT divided by N into M. Also put the values of this small n is capital N upon capital N into A, where Na is the Avogadro's number. Therefore, V bar square is equal to 3 nRT divided by Nm into Na. N cancel. Also put the value of Na into M is equal to M0. Therefore, V bar square is equal to 3RT divided by, instead of Na you can put M0, or finally taking square root of both sides. Therefore, square root of V bar square is nothing but VRMS is equal to under root 3RT upon 0. This equation, under root V bar square is equal to VRMS, or RMS speed or RMS velocity of gas molecule is equal to under root 3RT upon M0, where R is the constant, T is the temperature, and M0 is the molecular weight of the given substance. Now Also we discuss the another small topic is also related to equation of pressure of the ideal gas. This is nothing but interpretation of temperature in kinetic theory. Also, we can assume or consider the pressure equation P is equal to 1/3 m upon V into Q bar square. Or this gives PV is equal to 1/3 Nm into Q bar square. The 1/3 can be written as PV is equal to 2/3 into N into half M Q bar square. This 1/2 can be written as 2/3 into 1/2. 1/3 लाच आपण 2/3 गुणिले 1/2 परत 2 कॅन्सल म्हणजे थोडक्यात ही स्टेप आपण दुसऱ्या पद्धतीने मांडली. Then we get this term 1/2 m Q bar square is nothing but the kinetic energy or average kinetic energy of molecules, and the total average kinetic energy, the total average energy is E equal to N into half M Q bar square. This is the total average energy. Therefore, this equation becomes PV is equal to 2/3 into E. PV is equal to 2/3 into E. Also using ideal gas equation, using relation PV is equal to PV, that is pressure and volume, is equal to 2/3 into average total energy, but using relation, that is ideal gas equation, this ideal gas equation can be written as PV is equal to N kB into T, where this kB is Boltzmann constant, or this is equal to, from this equation PV is equal to, suppose this is equation number 1, this is equation number 2. PV is equal to 2/3 into E, and PV is equal to N kB into T. Therefore 2/3 into E is equal to N kB into T. Therefore, we find out the values of energy, that is E, or this E equal to 3/2 N kB into T. This is the equation of total or average total energy. Or this equation can be written as E divided by N. E divided by N is equal to 3 by 2 kb into T. E upon N is equal to 3 by 2 kb into T. Hence, this energy or average total energy is directly proportional to temperature. This 3 by 2 and kb is constant. Hence, this energy is directly proportional to temperature. This is about the kinetic theory of that gas molecule. Also, we discuss the small topic, that is what is meant by specific heat capacity. Specific heat capacity. In standard 11, we already defined this specific heat capacity. We know that if we heated the gas molecule or gas, if we heated the gas, its temperature of gas is increased. If we heat the gas, then temperature of gas is increased. And it is observed that very small rise in temperature, the large effect or large change in pressure and volume of gas. Therefore, a small increase in temperature or rise in temperature of that gas, this causes the large change in pressure and volume, and such temperature is called such heat is called specific heat capacity. And the specific heat capacity are of two types. The first is specific heat at constant pressure, that is Cp, is given as Cp. And second type is specific heat at constant volume, that is Cp. The specific heat capacity are of two types. The specific heat capacity at constant pressure, that is Cp, and specific heat capacity at constant volume, that is Cv. In standard 11, we define both the capacities, that is Cp and Cv. In next topic, we discuss the relation between Cp and Cv. The scientist Mayer use or derive and obtain the relation between specific heat at constant pressure, that is Cp, and specific heat at constant volume, that is Cv. In next lecture, we discuss or we obtain this Mayer's relation, that is relation between Cp and Cv.